The previous video discussed a t-test where both the two groups being compared were of equal size. This video will discuss a t-test where the two groups are of different size. Imagine a breast cancer education program where women coming to a clinic are divided into two groups. There is a control group, shown here. The control group, when they come to the clinic, are given a short pamphlet explaining various information about breast cancer. The experimental group, when they come to the clinic, are given the same pamphlet, but also participate in a 5 to 10 minute discussion with the physician about the material in the pamphlet. At the end of their visits, both the experimental and control group take a short 20-question quiz about breast cancer. And what we have here are the scores, 1 point for each question, right, that the experimental and control group got on the test. In setting up this experiment, the physicians involved believed that they had time only to talk to a total of 25 women during the course of the experiment. As you can see here, the number in the experimental group goes down to 26, and since we start at 2, that means there are 25 members in the experimental group. The control group, on the other hand, does not need to be limited to 25 because the physicians don't have to interact with them. So the control group actually contains down to 40 women. Given that we have two different size groups, we need to use a different formula to calculate the t-test. The formula that we use to calculate the t-test in this case is given on page 288, equation 9.7. And what that equation says is that the t-value is equal again to the mean of one group minus the mean of the other group divided by the square root of the pooled variance multiplied times 1 over n for the first group plus 1 over n for the second group. The pooled variance is a fairly complicated formula shown below the main formula in 9.7. In this video, we're going to go through the calculation of that t-test and replicate the material shown in figure 9.7 on page 288. As that figure shows, we're going to begin with n for each group. The experimental group consists of 25 women, the control group 40 women. Then we're going to get x bar for each group, equal average for the experimental group, control shift down arrow, and equal average for the control group, control shift down arrow. Then we need the variance, what is called S squared in the figure, S hat 2. Again, it's equal to VAR for the experimental group, control shift down arrow, and VAR for the control group, control shift down arrow. And now we'll put in degrees of freedom, which is given as n-1 in the figure, but I'm going to put it as degrees of freedom. So this is equal to 25 minus 1, and I'll just drag this to the right. And we have the degrees of freedom for both groups. Now, part of the formula for the pooled variance is the degrees of freedom, that is n-1 for each group, times the variance for that group. So I will calculate that right here. This is n-1, which is the degrees of freedom given above, times S hat 2. And this will be part of the pooled variance formula that's given under the main formula in 9.7. So this value is equal to 24 times 7.13 for the experimental group, and I'll just drag this to the right, and it's 391.975 for the control group. Now the pooled variance, S hat 2, which is given in the figure in the book simply as S pooled, it's actually S squared pooled, or the variance pooled, is equal to the sum of variance for the first group plus the variance for the second group divided by the degrees of freedom for the first group plus the degrees of freedom for the second group. And it turns out to be 8.93. Now the standard error pooled is equal to the square root of the variance pooled times 1 divided by N1 plus 1 divided by N for the control group, and I need one more parentheses, and the result is 0.76216. Now the t-test is equal to the mean for either group. In this case, I'll use the mean for the experimental group minus the mean for the control group divided by the pooled standard error. And the result is 3.3. When we get the probability of the t, the equal t-dist function, which takes the t-value, and degrees of freedom, which is the sum of degrees of freedom in each group, and I say I'm going to use a two-tailed test. But we see that the probability of a t-value as large as 3.3 is substantially less than 0.05. So we would conclude that we would reject the implicit null hypothesis that the experimental and control group are the same, or alternatively the implicit null hypothesis that score on the exit test is independent of the two-level categorical variable experimental or control.